Good morning, everybody. Today we're going to be talking about the second part of section 14.2, which is on probability. One of the big things I want to do today is just quickly review what we talked about last week and then get into some more complicated cases. And the two we're specifically going to talk about are conditional events, or what happens when one thing affects the probability of another, how to compute to deal with that, and then how to compute probabilities for non-mutually exclusive events, and we'll review what that means before we get to that. So first things first, as a review here, we talked last week about probability, and the most basic understanding of probability that you have to have is this idea that the probability of an event, a specific event happening, is the number of ways that it can happen, the thing you want to happen, so the number of desired outcomes over the total number of outcomes. So if you're looking at the probability of rolling a 1 on a die, there's only one number 1 on the dice, but there's 6 possible outcomes. So we have 1 out of 6. And that works pretty well for most things that we can reasonably count. So then we moved on to talking about multiple independent events. And the big thing we had to talk about was what this idea of independent meant. When two events are independent, it means that one outcome doesn't affect the other, doesn't affect the next one. And so things like rolling a dice 2 times would be an example of independent events, because just rolling the dice the first time has absolutely no effect on what happens the second time you roll the dice. Flipping a coin multiple times, doing anything multiple times is going to be a great example of independent events. So, a few just examples here, I guess. First one I want to do, and I'm going to have the video pause between each of these so that you can, think about these on your own. So the first one, probability of drawing a face card from a standard deck. Okay, so this is just one of your kind of basic understanding of probability questions. It's going to be a fraction. We need to think about the number of possible ways we can get what we want. So for face cards, we're talking about all the jacks. It's 4 jacks, 4 queens, 4 kings. So there's a total of 12 face cards out of 52 possibilities. And so that's our probability. Now we'd want to simplify that as much as possible, which ends up being 3 out of 13 when we simplify it. Or we could leave it as a decimal. That would be fine too. But we always want to simplify those fractions if we can. I'm going to actually pull up a calculator here. We'll use the scientific one. That'll be good enough for now. Okay, and then we'll take a look at something like this. What's the probability of drawing a king, then rolling an even number? So the biggest thing to understand here is that these two things are independent of each other. Drawing a king from a deck of cards has absolutely nothing to do with rolling a dice. So we'll start off with our king. There's 4 kings out of 52 cards. 52. And then our independent events rule is that we multiply. Then we're rolling an even number on a die. So there's 3 even numbers, the 2, the 4, the 6, out of the 6 total possibilities. And we'll multiply those together. This is a good place just to grab a calculator. 4 out of 52 times 3 out of 6, which is obviously just 1/2. And that tells us that our probability is 0.38, or if I turn it into a fraction, 1 out of 26. If you think about that as a percentage, you got about almost a 4% chance of that happening. Okay, and the last one here, this is a little bit different and kind of goes into what we're going to do today. The probability of drawing a 4, so drawing from a deck of cards a 4, and then drawing a face card. And so this one's a little bit different. The biggest difference here is that once you draw the 4 out of the deck, that's going to change the probability of you getting that face card. And so the probability of drawing the 4, well, there's 4 total 4s in a deck out of 52. Now when we go to draw our face card, there's not 52 cards anymore. We've drawn our 4. There's still our 12 face cards, but now we're only out of 51 of those cards. And the big difference here is the effect that drawing of 4 had on our next thing. We can still use the multiplication rule, but we have to adjust for that. We have to adjust our denominator here because there's only 51 cards left. We'd have to do a similar thing if I wanted to know the probability of drawing 2 face cards in a row. Let's do that example really quick. Drawing 2 face cards in a row. The first face card is just like we've been doing. There's 52 cards, and 12 of them are face cards. And to adjust for the second card, we assume that we've already drawn our face card out. After we make our first face card or pick our first face card, there's 11 face cards left out of 51 cards total. Now, one thing you're going to want to look at on something like this is you're going to look for words like with replacement or without replacement. Both of these are examples of without replacement. And what that means is we didn't put the first card back, and so it had an effect on the second card. If I just change this, drawing 2 face cards in a row with replacement. Now that means that I'm putting that face card back into the deck after I draw it. So my first one's the same. I have a 12 out of 52 chance. I've drawn my face card now. But now that I've drawn that face card, I'm going to put it back in the deck. And the difference there is that for the second face card, I now have the exact same probability of drawing that card again, or a face card again. So I put that one back. There's still 52 cards. There's still 12 face cards. So those last couple examples are an example of what we call dependent events. And as you kind of see there, they're not really all that much harder than independent events. You just have to take into account the first thing happening. So I should say last week. We did this last week with the cards. It's basically when the first experiment affects the next experiment. And so we have the probability of A and B, which is the probability of A and B happening, is the probability of A times the probability of B given that A has already happened. And so all we do is we assume that first thing we wanted to happen already happened, and we multiply by the probability of B happening now. We just have to adjust for it. And so this formula looks a little bit complicated, but it's exactly what we did with those cards. If I draw the 4 first, adjust the probability on the second one to assume that we've already drawn that 4. So here's a classic example. We've got marbles in a bag. So 15 marbles, 5 red, 6 green, 2 black, 3 purple. What is the probability of picking 3 red marbles in a row? We've got 2 different cases, and this is the idea of with replacement or without replacement. So the A says if the marble is put back each time. So go ahead and think about that. So if we put the marble back each time and we're picking 3 red marbles, the first marble we have a chance 5 out of 15. And then for the next marble, well, we put the red one right back in, so the next one's going to be exactly the same. We still have a 5 out of 15 chance. And then for the third marble, we have another 5 out of 15 chance. And when we multiply those all together, it's going to be a pretty small chance here. That's 5 out of 13. I could do cubed here, but I'm just going to multiply them out. 5 out of 13, 5 out of 13. And you'll see we've got a 0.056 chance, about 5.6% chance. So pretty low chance, but that's with putting the marble back each time. In other words, with the replacement. Change the color there. With replacement. Now this second one here is slightly different. If the marble is kept out each time. So we pick a marble, pick a marble, pick a marble, never put it back. So our first one doesn't change. Still 5 out of 15. But the second one we have to adjust for. If we assume we've already picked that red marble out, there's only 4 left. But in our favor, there's only 14 marbles now. And then for the third one, we assume that we got the second one as well. There's 3 marbles left, and we want to pick out a 13 now. So this is the probability for the first marble. This is the probability for the second one once we've kept that first one out. And then this is the probability for the third one, assuming that we've kept those first 2 out. And so let's take a look at what that does for our probability. We have 5 out of 15 for the first one, 5 out of 14 for the second, not 5, 4 out of 14, and then 3 out of 13. And you'll see our probability went way down, 0.021 as our probability there. And that's just showing this idea of the fact that there's less and less red marbles if we keep those out have a big impact on that. Okay, now this is probably the most complicated part of this, or at least hardest to keep your head wrapped around. And this is the union of events, or the idea that we could be talking about a probability of this or that happening, one thing or another thing. And there's 2 examples here, and one of them is a whole lot easier than the other. So we'll start with that first one. If the events are mutually exclusive, we just add the probabilities. And what that means is they can't both happen. And you'll see that in the example of what that looks like. So let's take a look at mutually exclusive events. So here's an example of mutually exclusive. And I like to draw these Venn diagrams. You certainly don't have to, but I do think it's helpful. So find the probability that a card is drawn at random is either a club or red. And the biggest thing you have to think about with these is, again, the idea, are they mutually exclusive? Is it possible to draw a card that is a club and red? And it's not, because all the clubs are black cards. So when we go to list, if we wanted to list these all out, we could. There's a lot of them. There's obviously 13 clubs, 1 through ace through king, and for red cards, there's ace through king of hearts and ace through king of diamonds. But we can just add these 2 probabilities together. So the probability of drawing a clubs, well, a quarter of the cards are clubs. So we have a 13 out of 52 chance, which is 1 out of 4. Out of 4, and draw 4. And then for our red cards, 26 of the cards are red, which is 1/2 of the cards. Now the big thing here is we're only drawing 1 card. We are not drawing a card. It's not the probability of drawing a club and then a red card. It's a probability that you draw 1 card, and it's either clubs or red. And so in this case, all we have to do is just add these 2 together. 1/4 plus 1/2 is 3/4. And there's other ways to think about these too. If you were to go through and say, well, how many cards are either club or red, and then take that out of 52. Well, either club or red, there's 39 total cards. 39 out of 52 is 3/4. Now, where this gets a lot trickier is when these events are not mutually exclusive. And that means that it could be both. And so again, we're going to go with the cards because that's the easiest kind of situation to deal with here. If the events are not mutually exclusive, we need to make sure that we don't count an outcome twice. And so what that looks like is something like this. We want to find the probability that a card is either a face card or red. And the big problem here is that there are red face cards, and we don't want to count them twice. If all we did was just add these 2 probabilities together, we'd be adding in those red face cards twice. We don't want to do that. So I went ahead and just put that up here. We have a little Venn diagram here. So we've got all the face cards in this circle, and you'll see there are 12 of them. We've talked about that before. There's all the spades, clubs, hearts, diamonds. Got my spades a little better this time. And then on the red side, we've got all the red cards. There's those red face cards, and then there's all the other ones, the ace through 10 of hearts and the ace through 10 of diamonds. So if I were to just add these together, well, my probability of getting a face card is going to be 12 out of 52. Or if I simplify that, that's going to be 3 out of 13. If my probability of drawing a red card, we just talked about that. There's 26 total red cards, so that's 1/2. Now, if I just added those together, the problem is that I've counted those 6 cards twice. It might be helpful here. This is 12 out of 52, and this one is really 26 out of 52. The problem is these 6 cards here, you can't see when I just point at my screen, can you? These 6 cards here are counted in here twice. So if I just added those together, I'd be counting all those cards twice, and my probability would be off. So what I need to do now is find the probability of my red face cards, or how many of those red face cards I have. And there's 6 out of the 52. Which ends up being 3 out of 26. Is my simplified version there. And so what I have to do is I basically just want to go through and not count these twice. So when I add these up, I'm going to actually use the 52s because those are my common denominators anyway. I'm going to take my 12 out of 52 plus my 26 out of 52, but I have to subtract my 6 out of 52. And remember, the 6 out of 52, that's coming from those face cards. I've counted those red face cards here. I've counted those red face cards here. This one just fixes it so that I'm not double counting them all. And I end up with 32, I believe. Yeah, 12 plus 26 is 38 minus is 32. So 52. And I believe that's 16 out of 26, 8 out of 13. And another way to think about this is you could actually go through and count all these cards. So all these red cards total up to 26. I'm not counting these again, 27, 28, 29, 30, 31, 32. There are actually 32 cards in this problem. And so we've got 32 out of 52. So you could just count up all the possibilities. The real difference here is just make sure you're not counting anything twice. And if you want the formula, that's the formula. Okay, now we've got one last thing here. Conditional probability. This is going to be a situation where we have additional information that change our probabilities. And so here's just kind of a simple example, and then I'll show you the formula if you want it. So find the probability that a card drawn from a deck is a 10 if we already know that it's even. And so what this does is we get some extra information, and we just have to take that into account. We know that the card is even. So that doesn't change the number on top in this case. So if I'm finding this probability that it's a 10, I'm thinking about how many different 10s do I have? Well, there's 4 10s. The fact that it's even didn't change that. But when I look at the bottom of this fraction now, that does get changed. Because we know that this card is even, there's no longer 52 cards. There's, depending on how you define that, I guess, you could say that there's 26 cards, or you could say that it could be just the 2s, the 4s, the 6s, the 8s, and the 10s, which would actually only leave you 20 total cards. So that's probably what they mean here. If it's an even card, there's only 20 total cards. Again, the 2s, the 4s, the 6s, the 8s, and the 10s of all 4 suits. That's 20 total cards. So we get a probability of 1 out of 5. So with that little bit of extra information, we know that there's a change to our probability. Now let's take a look at the mathematical definition. I would not use this. I find this confusing. So the formula here says the probability of A, given that we know B, is the number of ways that A and B can be true, divided by the number of ways that B can be true. And if we unpack that, that's exactly what we just did. On the bottom, we looked at the number of ways that the B part could be true. The B part here is the if we know that it's even. And so there were 20 even cards in a deck. The part on the top, the number of ways that A and B happen, is the part where we say we know it's a 10. So in this case, it's a little bit easier because all 10s are even cards, so we don't have to really adjust for that. But we looked at, well, there's 4 10s, so 4 on the top, and there's 20 even cards, so 20 on the bottom. The big thing here is when you're doing these kind of questions, still just think about them like normal probability. What's the number of ways that this thing can happen over the total number of possible ways? Just take into account the additional information that they give you. Okay, so these are going to be your homework. I don't think most of you have your books, so I'll put them on the worksheet and put them down below the link for this video. And remember, we have office hours on Tuesday from 9 to 10 and on Thursday from 1 to 2. A couple of other things. Remember that I put feedback on your assignments, so you can go into Canvas and look at the feedback, see which ones you missed if you have any questions. And you can fix those and turn them in again if you want to get back some of those missing points.